Hello. Good afternoon, everybody. I hope you're ready to take a nap with us because, as you can see, it's a very napping kind of mood over here. And the kitty cats are on me, so I'm quite a bit of under the blanket and under some layers of kitty cats. So I will be sitting here with you, hanging out and talking and catching up. And I do have some astronomy material pulled up as well that I want to cover today. But welcome, welcome. Good afternoon. We are live. If you're joining, thank you so much for joining and welcome to the live. Please do feel free to put something in the chat. I will read your comments and chat messages. It is a little bit early for us right now because we generally go live later in the afternoon or the evening or dead of night. But I was kind of already in this particular position, and here is Fuji Suji Baji taking their nap. So I thought maybe this is a good enough time to go live and cover some topics with you. And also we can hang out with the kitty cats. So again, welcome, welcome. Welcome to the live. And if you're seeing this as a video upload later on, thank you so much for watching. Do hope that you will hang out and chat with us till the end. Stay with us till the end and leave a comment if you're seeing this later on. And generally, when we start to cover the topic, there are breaks to discuss things and so on and so forth, you can always rewind and go back into the live and see the material from the beginning. So we will get started. I will share the live here soon on my other device. And let's see, I'm carefully taking my book off of the coffee table and putting it to the side here so that I don't disturb any kitty cats from their naps. Hello, welcome, welcome. Thank you for joining. How are you guys doing? Hello. We are live. Welcome, welcome. Just getting started. I'm going to share the live on my iPad here. Hello. How are you? Ooh, and then if you generally come to the live at night, hi Red Cross. Thank you so much. Red Cross says so cute. Thank you. How are you, Red Cross? We are getting ready for a big snow day tomorrow. And so in preparation of that, I'm doing a few things, but at the moment I am under the kitty cats. I wanted to get some grocery shopping done, some general preparation work done for the big snow day in Boston tomorrow. Tomorrow it's going to be snowing in Boston, and we will get a few very cold days as well. So that's mainly what I have in mind as far as preparing for the that stuff today. But right now we're live. I am unable to get up. They both sleeping happily. Yes, 1, 2, 3. There is 3 here with the thanks to the universe. Thank you so much, everybody, for joining. Red Cross says, so cute. Fine, what about you? I'm good. Thank you, Red Cross. Sleeping happily. Yes. Hi, Najib. How are you doing? Hello. So let's see. I will share the live on my channel. And I'm happy to catch up with everybody who is joining the live right now. Thank you for these many, many shapes. Thank you. Good seeing everybody here. And if you would like to put something in the chat so I can read your chat message, that would be awesome. And I'll try so that it's not covering up. It would be great if it doesn't cover up every other message. So Red Cross says, thank you for carrying them. Oh, thank you. Thank you for being here, Red Cross. Okay. So let's see. We are live. I'm sharing the live. I'm sharing the live on my other device so that people get to know that we have gone live. It's an earlier time. Which country? Well, we're in Boston right now. That's where I live. So that's the location at this time. Where are you from? Everybody, feel free to share where you're from. I'm just dealing with a user timeout situation here. Okay, so we don't have mods right now. Usually I go live later. I'm trying to go live at a sort of more earlier time on the weekends because just trying out different times here. A while ago, long time ago, I used to go live at this time on Saturday, Sunday, and I would catch a lot of the I'm in India. Yeah, it's a good time for people to join, I think, from India, Pakistan, those types of places. And so I used to and made a lot of friends on the live actually by going live at this time earlier. But nowadays it's more of a later in the afternoon type of thing that we do, or evening or nighttime live. So pretty much that's generally how it be at this time. So, I'm thinking I'll get started on the topic for today and let's get this topic rolling, and we can always go live again later in the day too. So no worries. If you see this later on, then leave us a comment and we're happy to interact and find you live again later on. So today I'll recap what we've been kind of doing on the lives. Hi Cortex, hi Cort XYZ or Cortex YZ, how are you? So lately we've been covering a lot of astronomy topics and kind of like, thank you, Cortex says cute cats, thank you. So we've been covering a lot of astronomy topics, and lately we were covering the planets in our solar system. So we kind of went through the rocky metallic planets or the terrestrial planets. Those are Earth, of course, the one we live on, Earth, Venus, Mars, and Mercury. So we covered that, and we covered some details of these planets, and then we also covered the Jovian planets, which is the Jupiter-like planets, Jupiter, Saturn, Uranus, and Neptune. And then in the last couple of days, we also covered the moons of these planets. So moons of Jupiter and Saturn and moons of Uranus and Neptune. How many kitties? It's however many you can count in the live. You have to watch and see how many you find is how many there are. So that's what we've been doing, kind of concentrated on the planets in the solar system and their moons, because I realized that on this channel, I've been covering a lot of astronomy, astrophysics, cosmology, etc. All kinds of topics, really. And at first, the topics were more from the 20th century, so more like modern physics, things like the work of Einstein, the early work in 1905, special theory of relativity, photoelectric effect, Brownian motion, and then moving on to general theory of relativity from him, as well as the development of quantum mechanics in the 1900s. And then it kind of shifted more to a sort of the more recent topics that are happening in the world of physics and astronomy. More current topics, we moved towards discussing particle physics. More specifically, we spent some time on particle astrophysics and also quite a bit of cosmology, because this thing with the the contributions of Einstein really paved the way for a more modern cosmology approach and the ability to study the universe and its origin as well as evolution to its current state. So over the course of a few different live streams, we actually covered the study of the universe and the Big Bang nucleosynthesis, as well as things like the cosmic inventory, dark energy, dark matter, the fact that you need those things, those types of things. So we've been covering a lot of such topics. And then we, because particle astrophysics leads into basically studying astrophysics with the use of various particles, we also talked about certain interesting sources of extragalactic high energy particles, which would also be a way to study astrophysics basically. And we also talked about neutrinos and cosmic rays and gravitational waves and things like that nature. So after doing all of this, I realized that, well, even though I was covering quite a bit about the entire universe at a more, let's say, large scale, as well as some of these very distant sources and extragalactic objects, I actually had not covered too much about our own home solar system and not too much about our own, the planets that are here, nearby, not too nearby in the end, but our own solar system. So that's why I took some time to cover the planets and their moons. And now I'm kind of going back to stars again. So every now and then we talk about stars, the death of stars, supernova, as well as stellar remnants, basically the remnant that is left behind by a star that has died. We have spent quite a bit of time talking about these types of things, okay? So now we will delve further into this topic, and we've been heavily utilizing this book right here called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. So yeah, if this is coming as a shock to you, this is sort of a kitty cat channel, but we talk about physics, cosmology, astronomy, and astrophysics. Hopefully you enjoy all those things. Generally, they lead to interesting discussion and topics and whatnot. And we're trying out this new live time for this particular topic. We usually go live later at night and things like that, but that's okay. Here we are, and generally speaking, it's a relaxation, soothing kind of live. So even if you want to just listen in the background, that's totally fine too. So that's what we will do. Let me take a sip of my coffee, and then we will get started on properties of stars. So we won't talk about every property of stars, but we will introduce the topic and talk about some interesting things. And also, this particular chapter has a lot of very pretty pictures. So I figured it's a fun one to show at this time, because I was hoping to get a lot of younger audience and viewers who might find those to be interesting. Cat was a wonderful animal, unpredictable character. Thank you. So because we have a ton of, let's see, because we have, I forgot the thing I was going to say. I need to put the book down beside me. I want to get a sip of my coffee. Hi, Sachi. So this one is Sachi. Look at her little paw. It's a little paw right there. One paw, two paw. This one is Sachi, and this one is Baji, and this one is Fuji, my baby. And they're very much asleep right now. It's a good time to talk about astronomy because the kiddos are sleeping. So let's get going. Basically, this topic, we will look at some pretty pictures and hi, Yash. How are you? Long time no see, Yash. How are you? Very sweet. Yes. Hello. So, although astronomers study a wide range of objects, from dust grains to superclusters of galaxies, the study of stars and the laws dictating their behavior is a key part of astronomy. So we're reading from this chapter now. A star can be concisely defined as a luminous ball of gas powered by nuclear fusion in its interior. This definition distinguishes stars from smaller objects like planets and brown dwarfs that are too cool inside for fusion to take place. And it also distinguishes stars from stellar remnants like white dwarfs and neutron stars that were stars once but no longer host a fusion reactor in their interiors. So, I know we have defined what a star is in the past on this channel, but this is a really nice formal introduction to kind of present the material to you as far as what do we mean by stars. Definitely, just like our sun, pretty much to be a star that is alive and well, you have to be burning and producing heat and energy just like the sun does for us, and that's how we're able to survive. But the source of that heat and energy is generally nuclear fusion, and it is doing some kind of nuclear physics to convert some lighter elements into heavier elements. Our sun is converting mainly hydrogen to helium, so it is doing the nuclear fusion steps to get helium from hydrogen, and that particular step fuels the sun and also keeps it alive against its own gravity. So if a star runs out of its fuel or nuclear power, it will collapse under its own gravity, and that generally leads to a big explosion and the death of the star involving some kind of supernova. And that's a whole process in itself that we have sort of looked at as well here in previous live streams. And in the end, you're left with a stellar remnant. So these examples of stellar remnants, like white dwarf, neutron stars, and black holes, or the other example we said just now, brown dwarf or planets, like we live on a planet. Those are the distinguishing features. Like basically, a stellar remnant is not doing nuclear fusion, not to the extent of a star anyway. And basically, for a star to be a star, it has to do this nuclear fusion and basically has this fusion reactor in its interior. So that's what we mean by a star. And now we will learn a little bit more about them. So, astronomers have developed many methods of estimating distances to stars and other celestial objects. So, we want to figure out how far is a star and how do we generally figure that out. So that's what we will review here. We review only a few of the more useful techniques here for understanding how to get the distance to a star. Within the solar system, the distances between planets can be accurately measured using radar. A brief, powerful burst of radio waves is sent toward a planet using the dish of a large radio telescope to collimate the radiation. After a time delta t, a radio echo is detected, the time delta t, which can be measured with great accuracy, is the round-trip travel time for a photon. The one-way distance from the radio telescope to the planet is then d equal to c, which is the speed of light, times delta t over 2, because the photon traveled that distance and back. So we divide by 2 to get the one-way distance. Can I ask what is the conspiracy theory of aliens? Is it real or what? Well, I don't know about the conspiracy theory, but I think people are interested in understanding if there's life on other planets or other parts of the universe or even this galaxy. And for that, they look for planets that could maybe be sort of like the Earth, exoplanets basically, planets associated with other stars and systems, and to see if the conditions on those planets, from what we can observe and deduce, would they be suitable for life or not. So there is really, I don't know if there's a conspiracy theory really, but definitely it's an open question that we ask to see, which is there life on other planets or not? And for that, the first step is to kind of find such planets in the first place that would be suitable for life. So anyway, so this radar measurement thing that I was just mentioning is a good way to get distances between planets. Thanks to careful radar measurements, distances within the solar system are known with great accuracy. For instance, the length of the astronomical unit is known to better than 1 part per billion. So you'll hear me talk about this astronomical unit. It is the distance between Sun and Earth. And the number is very large, but I'll read it. It's 149,597,870.7 kilometers. So that's the distance between the Sun and the Earth, and we have given it this name, astronomical unit. And it's basically a unit of distance that we often use in astronomy because it gives you some reference with our own example, that is, the example of the distance between the Sun and the Earth. The radar technique for measuring distances is useful only within the solar system. Even if you had the patience to wait more than 8 years for a reflected radio signal from Proxima Centauri, the nearest star other than the Sun, the signal would be far too faint to detect with current technology. So this radar way of figuring out the distances, it makes sense within our own solar system. Even in our own solar system, these stars, or not these stars, the planets that are farther away, Neptune and Uranus, that they're quite far away. So it's good that we can use radar within our own solar system, but from other objects that are beyond our solar system, it doesn't really make sense because it would take very long for the radio signal to get reflected back. And also, it might be too faint. Thank you. Nice explanation. Thank you. Sure. Yeah. Happy to. So a useful tool in the astronomer's kit for measuring the distance to nearby stars is stellar parallax. So we will look at this for a little bit, but also note that after the Sun, the nearest star is Proxima Centauri. So soon we're going to actually talk a little bit about the nearby other stars. So, stay tuned for that. So we will see in short what this stellar parallax means, and that will give us a way to also measure distances. So stellar parallax is also a proof of the Earth's motion around the Sun, And the Earth's motion around the sun creates an apparent motion of nearby stars in a tiny ellipse. So, because we're moving around the sun, it creates this apparent motion of the nearby stars in a tiny ellipse. And something to do with that is going to help us with the distance measuring. So, the semi-major axis of the ellipse has an ellipse. Is of course a shape that's not quite circular. It's sort of, there is a semi-major axis and a semi-minor axis. And basically, a lot of the orbits of planets around the sun is elliptical. So if you're familiar with what an ellipse is, then you understand what I'm talking about here. And you have much knowledge in universe. You can join with Elon Musk. Thank you. So the semi-major axis of the ellipse has an angular size of pi seconds. And so we have this relationship between this angular size with the distance from the source. So if there's a parallax of pi star of a star, which is large enough to be measured with the equipment at hand, then the distance to the star can be calculated with this equation of d equal to a big number over the pi seconds. So basically this parallax helps us to measure the distance. And since we know the length of the astronomical unit very well, we're also taking into account that we know the astronomical unit because we have figured out how to measure the distance between us and the sun. Then the accuracy with which we know the distances to nearby stars is determined by the accuracy with which we can measure this angular size. The astronomical unit is an inconveniently small unit for measuring stellar distances. So our sun is quite close to us. So that's why, close to us, these are all relative things anyway, but our sun is much closer than any other star, really. So that's why the author is saying that there is sort of an inconvenience in how small it is. And so then they introduce this other stellar distance called parsec. So this is another thing that I have mentioned, and I probably say here and there what a parsec is, or sorry, that we use it as a scale of distance. But here's the definition in case you're interested, and now we will know what a parsec is. So astronomers tend to measure stellar distances in parsecs, even though we talked about the astronomical unit, and especially for our own solar system, you will see us using the astronomical units because as far as the planets in our solar system go, because the distance between the Earth and Sun is one astronomical unit, it's nice to use it as far as understanding the distances of the other planets as well. But when it comes to figuring out about the other stars or other galaxies and things like that, these things are so much farther away than us, than, say, the other planets of our own solar system, that we actually kind of need this other new or different measure of distance. Okay? And that is the parsec. So that is spelled as PARSEC, parsec. So let me read your comments. Okay, perfect. So the parsec is abbreviated as PC, and it's the distance at which a star has a parallax angle pi seconds equal to 1 arc second. So in metric units, this 1 parsec is 3.086 times 10 to the 16 meters. So pretty much, if you trust the people who are doing the math, all you really need to know is that a parsec is a very big distance, and the number is given by 3.086 times 10 to the 16 meters. And this angular size pi seconds that we keep mentioning here. Even for the sun's nearest neighbors among the stars is less than 1 arc second. So that angular size is not huge. When Frederick Wilhelm Bessel first measured stellar parallax in 1838, so as this is pretty old, as early as 1838 we were doing this. This guy, he found that the star 61 Cygni had a pi seconds of, or the angular size of 0.3 arc seconds. That's the size of a 1 cent coin, US or Canadian, as seen from 14 kilometers away. Currently, the best measurements of parallax angles at visible wavelengths are those made by the Hipparcos satellite, which measured pi seconds for over 100,000 stars in our galaxy, with a typical accuracy of a milli-arc second. So that would be 0.001 arc seconds. So basically, these parallax type angles or angular sizes can be very small. So we need all these definitions in place and understandings in place as far as when we say these things, so that you can understand what we're talking about and what distance, what sizes in the sky we're really talking about, right? So hi Shakuni, how are you? So the sun's nearest neighbors are the 3 stars of the Alpha Centauri. So I just mentioned Proxima Centauri. Let's consider our nearest stars now more fully. So the stars near us are the 3 stars, other than the sun, that is. The stars near us are Alpha Centauri system, they're called Alpha Centauri system, and this comprises basically the nearest of the 3 Alpha Centauri. C is known as, of course, Proxima Centauri, the most proximity one to us. From the Hipparcos measurements, we know the parallax, and that's the distance to each star in the system. So we've got the 3 stars are Proxima Centauri, Alpha Centauri A, and Alpha Centauri B. And we have some numbers now to give you an idea for how far they are. So Proxima Centauri is the angular size is given by 0.7723 plus or minus 0.0024 arc seconds. So pretty tiny sounding. And the distance is 267,000 plus or minus 800 astronomical units. So it's a distance that comes with an error, because this is a large distance, of course, away from us. Just for reference, Jupiter is 5.2-ish astronomical units from the sun. So, and Jupiter is pretty far away from the sun. So, I mean, we are pretty far away from the sun, and we are 1 astronomical units away from the sun. So 267,000 ish astronomical units is a lot. And that is where the nearest star is, other than the sun. So very far away, we are very lonely, and pretty much our solar system, us and the sun and the other planets are now going to seem much, much more closer together once you consider where everything else is, okay? Main बढ़िया, आप कैसी हो? I'm good, thank you. Then we consider Alpha Centauri A and B. Alpha Centauri A is, let's see. So here's the deal. So we have this number, 277,900 plus or minus 500 AU, or astronomical units. So Alpha Centauri A and B are even farther away. And they form a closely bound binary pair with an average separation of around 24 AU. So that's slightly larger than the distance between the Sun and the Uranus, Sun and our one of the planets in the solar system, Uranus. And so basically we're saying that Alpha Centauri A and B system is around, that number, 277,900 astronomical units away. and they form what we call a closely bound binary pair. But really, there is some separation between them. The average separation is 24 astronomical units, which doesn't sound like much at this time because we're considering distances that are hundreds, over 200,000 astronomical units away. But at the same time, 24 astronomical units is pretty large in the sense that in our solar system, that's where Uranus is, distance between Sun and the Uranus. And Uranus is not considered to be very close to the Sun. So it's all kind of relative, kind of, the way you want to think about it. You have good knowledge. Well, I'm referencing a book, but thank you. So Proxima Centauri, however, is zero. So Proxima Centauri is a little bit closer. We're seeing how much closer, right? So Proxima Centauri is 10,800 astronomical units closer to us than the Alpha Centauri A and B, and that in parsecs is 0.053 parsecs. So you'll see how the parsec unit is sort of more appropriate when you talk about very large distances and capturing sort of that relativeness, because when something is very far away and another thing is just a little bit more farther away, in the nearby proximity, those distances can be considered to be large. But from us, both Proxima Centauri and the Alpha Centauri A and B system are both really far away. And pretty much the difference in distances between them from us is 10,800 astronomical units, which sounds like a lot, but it's only 0.053 parsecs. So yeah, Proxima Centauri closer to us than Alpha Centauri A and B. In addition, Proxima Centauri is separated from Alpha Centauri A and B by, to turn the page to find out what this. Oh, wait. Now I've lost it. Interesting book arrangement. There are a lot of very pretty pictures, and then the text starts back up. So Proxima Centauri and Alpha Centauri A and B are more than 2 degrees apart as seen from Earth. So that's another way to kind of get this distance, the physical distance. So because there is this angular separation between Proxima Centauri and Alpha Centauri A and B from us, as seen from Earth, you can put that in, D is equal to the angular distance over that 265 arc second per radiance number, and all of that together gives you 10,200 astronomical units. So there's this other way of considering the whole thing as well. So the 3-dimensional, let's say, distance between Proxima Centauri and the Alpha Centauri A and B pair is 14,900 astronomical units, or about 0.07 parsecs. So even with the accurate angular measurements provided by Hipparchus, stellar parallax is useful only for stars within 200 parsecs of us. So this type of way of measuring, first of all, will come with an error, and it seems it's only going to be useful for stars within 200 parsecs. There is sort of a limit to how useful it can be. That's less than 3% of the distance from here to the center of our galaxy. Oh wow, Hipparchus measured the parallax of around 42,000 stars with an error of less than 20%. Compared to the estimated 200 billion stars in our galaxy, the number with distances estimated by stellar parallax is small. For the overwhelming majority of stars in our galaxy, we must develop techniques other than stellar parallax to find their distances. We will return to the problem of distance determination later in the text. For the moment, let us divert our attention to the problem of determining the brightness of a star. So, hi BJ. Hi. Hello BJ, how are you? So, this was to give an idea that even with the very nearby stars, there are some issues with utilizing stellar parallax. Sure, stellar parallax can give you an idea for how far things are, but because there are errors associated with stellar parallax way of measuring the distance, you just have to keep in mind that that cannot be used for every case. Because of this, so I'm reading a footnote now. Because of this definition, there are 206,265 astronomical units in 1 parsec, just as there are 206,265 arc seconds in 1 radian. So the angular, good night, my angels. Oh, yes. How are you, BJ? So this angular separation between two bright objects, 2 can be used. And from that, you might get that, you might get that it's kind of hard to do the distances. So next we will consider how bright is a star, because how far is a star seems like kind of a difficult question, actually. So anyway, let's now look at some pretty pictures. Look at that. Isn't that so pretty? So that is comet Ikea and the Andromeda Galaxy below. So here's a comet, and then here is the Andromeda Galaxy below it. So pretty cool picture. I think this chapter is actually kind of full of these pretty pictures. I might show more of these in my next live. Let me keep going here to see, actually no, here. Look at this. This is Uranus and Neptune. Uranus on the left, Neptune on the right, with the Earth shown on the same scale. And there is a decidedly blue color of Uranus and Neptune. Oh well, nice. So this chapter is full of a lot of pretty pictures, so we will show these at some point. In this chapter next, we will talk about how bright is a star, and there is a bunch of definitions for brightness: intrinsic brightness, apparent brightness, luminosity. We have talked about apparent magnitude of stars and supernova actually on the channel here, because those were very important in understanding the expansion of the universe, turns out, when we talked about dark energy. If you remember, if you were there for that. Basically, when we talked about evidence of dark energy, which of course has to do with the expansion of the universe, to prove out that the universe is expanding, they actually looked at a bunch of supernova data at different redshifts, and this quantity called apparent magnitude was very important there. So those are the types of things that we will look at next in this section. Then we will also talk about how hot is a star. And that's another complicated topic. Then we will talk about how big is a star and how massive is a star. Ooh, I like it. Ooh, and then, you know what I might do? Some of it I might skip and talk about visual binaries. So if you know about the Sirius system, you might have heard about the Sirius star. The Sirius system is actually an example of a binary. So it was realized in the 19th century. Fun fact that the star we know as Sirius has a much fainter companion. So we thought that Sirius was just one star, but actually it is a binary. So the more luminous component of the binary system is now known as Sirius A, while its dim companion is called Sirius B. At visible wavelengths, Sirius A is roughly 1,000 times brighter than Sirius B. At X-ray wavelengths, however, Sirius B is the brighter of the two. So visually, because we can see with visible light with our eyes, we thought it was just the one because we don't have X-ray eyes, and Sirius B is brighter. Is brighter in X-rays. So fun fact. And indeed it is a binary. Look at that. There you go. Sirius B with diffraction spikes and Sirius A above and to the right as seen in X-rays. So look at that. In X-rays, Sirius B is really bright. Wow. I didn't realize it was so much brighter. I knew that there were the two, but I didn't know that Sirius B was so much brighter in X-rays. Wow. That's fascinating. So we might come back to this. It's a good thing for me to look at what stuff is where. I'm just exploring the chapter with you right now. But basically, we might come back and talk about the Sirius binary system, spectroscopic binaries. Oh, I love it. There are actually so many more binaries than just the one stars. A lot of people, a lot of stars are actually binaries. That's amazing. Okay. All right. You know what? So I think I get a pretty good idea. I think I'm going to continue. Thank you, everybody, for joining. I think I'm going to continue the topic at a later afternoon, evening live, and we will pick up on this particular topic, properties of stars. At the moment, we will continue to nap, and thank you so much for being here, and thank you so much for joining us for this quick live session. Appreciate everybody for being here, and if you have any fun star facts to share with us, please do so in the comments and chat here, and we will read them as we keep going forward. So, thank you. Oh, Fuji Suji Baji heard something. He's thinking, she was like, what is it? What is it? It's okay. It's okay, Suji. Baji. You nap. You nap. You take a nap. Ooh, and if you're joining the live, could you please like the live? If we could get 10 likes, that would be amazing. Thank you so much. Oh my gosh. Oh, Fuji.